Hello everybody, this is Abdallah Sobehy, a PhD student from Telecom Paris. Today I'm going to be presenting my article on indoor localization using channel state information of MIMO antenna. This is prepared for the International Conference on Communications, ICC 2020. So without further ado, let's hop in. The article presents our k-nearest neighbor solution applied to indoor localization. It's based on channel state information of MIMO antenna. This work has been conducted under the supervision of Renault from Telecom Paris and Paul Mühlethaler from INRIA. So the plan of the talk is as follows. First, to introduce the localization problem and shed light on its tremendous applications. Then we briefly introduce the channel state information, also known as CSI, which is the main input to our learning model. After that, we concretize the context of the problem by presenting the public dataset made available by the Communication Theory Workshop for an indoor positioning competition in which our solution achieved the first place. After that, we introduce the methodology, including mainly 3 steps: data preprocessing, input feature selection, and neighboring criterion and k-value selection. Finally, we compare our results with state-of-the-art solutions applied to the same dataset. Let's start by defining localization. It is the process of determining the position of an entity in a given coordinate system. It has a wide range of applications, starting from Internet of Things, mobile ad hoc networks, vehicular ad hoc networks, and industrial automation. Even though a lot of research has been conducted in this area, the localization problem remains unsolved. This is because different contexts has different input parameters, different sensors used, and different constraints. For simplicity, we can think about the indoor context and the outdoor context, where the constraints are totally different. Let's have a look at some of the applications. For example, autonomous driving. A car needs to know precisely its location and also the location of other cars to be able to park. And more importantly, to know the location of pedestrians to avoid having accidents. Also, localization is used to power routing algorithms based on geographic location. If a node X wants to send some packets to node D, using the location of intermediary nodes, it can make an informative decision on the best path to follow. Here we have a look at Amazon's robots that are used to automate the process of transfer of products from one place to another. It's clear that the robots needs to know exactly the position of the shelves to be able to move them. Since we saw different applications to localization, let's now have a look about the different sensor information that can be used to achieve localization. For example, vision sensors, such as camera or lidar, is used to monitor environment frequently, and by matching the changes that happens to the environment, different solutions can conclude the movement of the robot that led to this change. There is also the well-known global positioning system, GPS. However, you can think that in the indoor context, it does not work, it only works in the outdoors. The next 3 examples are in the category of localization known as range-based localization, where the distance between an entity and the other is concluded based on these criteria. For example, RSSI, received signal strength. This is widely used in the state-of-the-art solutions because it's easy to obtain and does not require additional hardware. There is also the time of arrival, which is more accurate but requires synchronization between communicating entities. And finally, there is also the angle of arrival, which computes the angle from which a signal has arrived. So channel state information is a complex number, and it describes the channel's effect on the transmitted signal. This can be, for example, the fading or scattering. This equation formalizes the channel state information effect. As you can see on the left-hand side, there is the received signal. We'll get to the I and J subscripts in a minute. Then on the right-hand side, there is the transmitted signal, which is multiplied by the channel state information, and then some white noise is added. Some of the characteristics of the channel state information is that it's calculated at the physical level per subcarrier. This means in the OFDM context, where signals are transmitted on various subcarriers simultaneously, a much more richer information is obtained. This means that for each subcarrier, there is a channel state information that can be calculated. It is more stable when compared to RSSI, and thus it allows for more accurate mapping between position and the CSI values. Since CSI is a complex number, it can be presented both in the polar format, as in the magnitude and phase, or the Cartesian coordinate system by presenting its real and imaginary parts. The I and J subscripts are here to represent two factors. First is this number of sub-antennas in the MIMO context. So, for example, the I would represent the CSI calculated at each of the antennas of a MIMO antenna, and the J would represent the subcarriers on which the orthogonal frequency division multiplexing scheme was used. In this figure, we show the variation or different values for the four components for around 900 subcarriers. So the communication theory workshop prepared an indoor experiment where a 2x8 MIMO antenna found in the corner of this image is set up where 924 subcarriers are used, and there is a white box which represents the transmitter that is moving along a 4x2 meter table. The main carrier frequency is 1.25 gigahertz, and we are provided as contestants with 17,000 samples, where the channel state information is matched to the position of the transmitter using a tachymeter of around 1 centimeter error. The first step in our solution is to choose the input to our learning model. So since we have four components, magnitude, phase, real, and imaginary, we want to choose one or two of the most stable components. These four figures represent readings from the four components recorded at the same position but at different times. We can see that at the most left, the real component, the values differ for the same position. The same with the imaginary, but we can see that the magnitude, they are almost superposing, which gives a good sense of stability, which is not the case of the phase either. In order to reach a more rigorous decision about the stability of components, for each component, the mean correlation coefficient is computed between samples recorded from the same position but at different times. The figure on the right here shows the mean correlation coefficients and the error bars for each of the four components. It can be clearly seen that the magnitude component has the highest correlation coefficients, which led us to decide to use it as the input feature because it manifests the highest stability. The next step is data preprocessing. Since we choose the magnitude, now we have 924 subcarriers for each of the 16 antennas. This is still a huge number of input data for only one position. In order to reduce both the noise and dimensionality simultaneously, we first do a polynomial regression to fit a line through the input data. As shown by this example, the red line is fitted through the blue raw data. And instead of taking all the 924 subcarrier points, we only use some equidistant set of points along the red line. In order to choose the degree of the polynomial, we made some experiments by fitting the magnitude using degrees of 3 up to 8 and seeing the mean error and the mean standard deviations between the fitted line and the raw points. And it can be seen that at degree 6, the error begins to stabilize. That's why we chose it as our polynomial degree. Empirically, we chose to select only 33 points of the 924 subcarriers. In conclusion, using this method, we reduce both the noise and dimensionality by a factor of 28. Since we have our data cleaned and preprocessed, now to build the k-nearest neighboring model, we need to choose first the neighboring criteria, then the number of k values. So let's consider two samples, M1 and M2. Each represent the magnitude values of the 16 antennas over the 33 equidistant subcarriers along the polynomial fitted line. We propose three closeness criteria. First, the absolute difference, and the Euclidean distance, and finally the correlation coefficient. In order to decide on the best criteria to use, we perform different experiments with different number of antennas. So on the x-axis here on the right figure, you can find the number of antennas that we use, and on the y-axis you find the mean square error of the predicted position. The predicted position is calculated using a very simple rule. For each test sample, the sample in the training set that yields the smallest neighboring criteria value is simply chosen to be the estimation. And we can see here that the Euclidean distance criteria yield the smallest error, and it's also very fast to compute. That's why we choose it as the neighboring criteria. Next is the choice of the k-value. K-value represents the number of neighbors considered to estimate the position. Here on the right, we can see the figure of using different k-values. You can see that using a k-value of 1 yields the smallest mean square error. That's why we make a choice to use a k-value equal to 1. Now we compare the results of the k-nearest neighbor solution to other state-of-the-art methods applied to the same dataset. NDR uses a multi-layer perceptron neural network on the magnitude component. Ensemble uses a number of MLP together to enhance the estimation. CNN uses a convolution neural network on both the real and imaginary components altogether. Our k-nearest neighbor solution achieves an error of 2.4 centimeter mean square error, which yields a total of 16% improvement over the second best solution, which is the ensemble neural network. It can also be seen in the figure that increasing the number of used neighbor antennas, generally the estimation improves. However, this is counterintuitive when only 2 antennas are used with the k-nearest neighbor. So this gives a hint that k-nearest neighbor is sensitive to the number of training examples. Finally, we study the error distribution of the test set. On the left figure, you find on the y-axis the frequency of errors, which is log-scaled, and on the x-axis the mean square error of each of the 1700 test samples. It can be seen clearly that most of the errors are very, very close to 0, and only very few outliers are spread along the length of the table. On the right figure, the Euclidean distance of the channel state information between the test sample and the closest sample in the training set is compared against the mean square error. So on the x-axis, you find the Euclidean distance between the channel state information to the closest training sample, and the y-axis represents the corresponding mean square error. It can be seen, and it goes with the intuition that the closest the Euclidean distance, or the smaller the Euclidean distance between CSI, corresponds to a smaller mean square error, which is the case, because you can see as we go to the right of the figure, there are more, the larger the Euclidean distance to the closest training sample, you begin to find outliers where the error is 1 meter, 2 meters. So the main conclusions of our work are: channel state information is a detailed, granular, and a stable parameters that can be used efficiently for localization. Using statistics, we showed that the magnitude component shows the highest stability among the 4 components. With the k-nearest neighbor method, using the Euclidean distance as the neighboring criteria, and with the k-value equals to 1, we were able to achieve a 2.4 centimeter mean square error, outperforming state-of-the-art solutions. For the future work, we believe that using more data, especially in the non-line of sight scenario, we might be able, with further studies, to detect outliers before making the position prediction. Here are some of the references used in the making of this presentation. In the end, I would like to thank you for your attention. And if you would like to know more details about the indoor positioning competition, kindly scan the QR code available here. And for questions, whether during the conference or afterwards, you can find my LinkedIn profile using this QR code, and I'll be happy to answer any of your questions. Thank you for your attention.